So for any of you who don't know me, I am Stuart Sierra. I work at Relevance. I'm a Clojure contributor, author, general fanboy, and I have a talk here that I've called Thinking in Data. So there's this word that gets thrown around a lot, functional programming, pure functions. We talk about these things a lot in context of Clojure, but what does it really mean? What is functional programming? Every programming language has functions. Lots of programming languages have higher order functions. So what is it that makes functional programming special? And by the way, I don't have an answer to this question. I just thought it would be provocative to start with something rhetorical. So instead, I'm going to talk about this thing that I came up with called data-oriented programming. Now, this is not a paradigm. I am not going to be publishing Teach Yourself Data-Oriented Programming in 21 Days. There isn't a lot of theory or, really intense mathematical thought behind this. This is more a set of conventions, rules of thumb, things that I have personally found useful working with large projects in Clojure. And it has a lot of benefits. The most important one, that it makes your programs easier to understand, easier to reason about. The primary difficulty we have with programs is just understanding what they do, trying to visualize what the processor is doing 1 billion times a second. We can't see that. So we have a hard time sort of visualizing it in our minds. Now, I promise that this is not going to be an extended rant against object-oriented programming. There will be aspects of ranting to it. But, I think we've definitely been trained in this paradigm. Anyone who's done software in the past 20 years has been trained this way, to think of programming as this collection of objects. But, this works well in a lot of scenarios, but the fundamental fallacy, I think, of object-oriented programming is that you can program with objects. Anybody ever, dereference a pointer and, something lands on your desk? We don't have objects in the computer. We have data and code, and they might interact in a way that resembles objects. But the world is made up in objects in a very different way from the way object-oriented programming models them. So we find, or at least I find, that objects tend to work really well for things that exist entirely within the computer. Things like stacks, queues, GUIs, widgets. Those live their entire lives inside the computer. They don't exist anywhere else. And objects are, a pretty good fit for those kinds of things. Where I feel like this model really breaks down is when you're trying to make objects for things that exist in the real world. And, this is where every programming textbook starts. You have an object like a person, a manager, a product. But those things don't live inside the computer. What you actually have in those objects is a representation. You've got data. You've got some piece of information that represents something in the real world. And you might need different representations for different tasks that you have. So if you have, an object representing a customer, well, you might have one representation of that customer with things like their shipping address and their billing details, and you use that for your ordering. And then you have another representation of your customer that has their complete order history, everything they've ever bought, and you'd use that for your sales and analytics. And when you try to pile both of those things into the same object, you end up with, big bloated classes that are really difficult to work with and hard to upgrade. So I'm going to offer working with data as a way to avoid some of those pitfalls. And the number one point that I want to drive home in this talk, if you take nothing else away from this talk but this one idea, let it be this: make your data visible. We can't see what computers do. When we're trying to debug, it's like a particle accelerator. Those particle accelerators, they accelerate these little microscopic things to a fraction of the speed of light. They crash them into each other, and this all happens in a fraction of a billionth of a second. And afterwards, they have the splatter patterns that those particles made on the wall. We have stack traces. We have logs. Those are our splatter patterns on the wall of our particle accelerator because we can't see What's going on? Computer does a billion things in a second. We can't see that. All we can see are the results. But if we design our programs in a way that they produce more visible things along the way, then we can have a much easier time understanding what our programs are doing and where possibly they've gone wrong. So, of course, in a dynamic language like Clojure, the number one tool for doing this is the REPL. We can explore our programs. We can try things and play around. So here's a very simple example. I've copied up here a somewhat naive implementation of the frequencies function in Clojure. This is a pretty simple function, a very useful one, that counts up the number of occurrences of items in a collection. So I might write this function and look at it and say, yeah, I think it looks right. And then I try it in the REPL with a small example case. And I can look at that and say, yeah, that looks right. I think the function is doing what I want it to do. But I could also, formalize this in a unit test and add a few more cases and gradually try to convince myself that the way I've written this function is correct. But I don't really know what's happening inside this function. I don't know what is going on in particular in this reduce. Reduce is a loop, and there's something that's happening at every step of that loop, but I don't really know what it is. So I can make one little change to this function. I could swap out the reduce function for the reductions function. Reductions is just a variant of reduce that rather than returning the final result, it returns a sequence of all the intermediate results. So then I could use this to test. I could add in the pretty printer and run my function again. And look at this. I get a nice little log of everything that happened in my function. And I can see, okay, I started with an empty map, and then I counted one A, and then two A's, and then so on. And I can actually look at each state that happened during the execution of my function and use that to validate my assumptions, to verify that the way I think this function works is, in fact, what it's doing. And I've actually worked on some moderately large systems that work this way. We had a calculation that was essentially a big reduce. Turns out you can represent almost any kind of loop as a reduce if you really want to. So we just took a modified version of that calculation, stuck a reductions in there, and then pretty printed all of the intermediate states, everything that was happening in our program as a sequence of values over time. Where have we heard that before? So this is very useful. You combine just these two simple things, a pretty printer and reductions, and you can visualize what's happening in your program. But of course, eventually the state gets too large. And this happened to me in this system I was working on. We got more and more state added to the intermediate stages, more and more things to keep track of, and eventually the pretty printed output was thousands of lines. We had just one state of the program occupied several screenfuls of information. So we couldn't just look at that anymore and tell if it was correct. So we added another layer of abstraction. This chart here is a poker game. In fact, it's all of a poker game, the entire thing from beginning to end. So I was working on a system for playing card games, an online gaming system, and we were started out by printing out the states of our system and all of their intermediate steps and looking at them to see if they were correct, but eventually it just got too big. We couldn't process the information we were getting from the computer. So we took a couple of hours and wrote some really dirt simple code. I mean, like childishly simple code to print out an HTML table of the same information that was in those state maps. And we didn't put a lot of effort into making this look good. You know, this is not something that a designer worked on. We're just a couple of coders. We needed to throw some information into a table so we could look at it. But we were able to then visualize everything that happened in a trial run of our gaming system. And basically, this table is pretty simple. Each row is a state. one discrete state in the evolution of our program. The first column is something that happened, whether it's input from the user or something the server decided to do. They're color-coded. The next column is what the server thinks the state of the game is, all the information the server has. And then the remaining columns are what each player's view of the game is. So one of the things we wanted to validate here was that the players are not being given more information than they're allowed to have. So we wanted to see that the player's view of the world was being consistent with the server, but that it wasn't allowed to see certain information. And doing this, like I said, this was really easy code to write. It took us maybe a couple of hours. And we got more leverage out of this. We learned more about how our program worked, and we found more bugs doing this than if we'd spent all day writing unit tests. But I'll have more to say about tests. Another thing I've come to discover that really just, I don't know, this feels like a rule of thumb, but it seems like almost everything in my programs now is a map. Like any object I have, any piece of data I want to represent, I can put it in a map, and it's a pretty good fit. Steve Yegi wrote a great article some years ago called The Properties Pattern, where he basically said, the thing that every program ends up needing is this collection of key value pairs. And you can call it a map or a dictionary or in JavaScript an object, but it's always just keys and values. We need that in our programs. But what I discovered is that once I started thinking about lots of things as maps, I realized that everything, in a way, is kind of a map. You think a mathematical definition of a map is a function that maps from keys to values. And in Clojure, this is literally true. Maps are functions from their keys to their values. So it's sometimes interesting to think about the other collections as just degenerate cases of maps that have different constraints. So, a map goes from arbitrary keys to arbitrary values. A set just has the values map to themselves. And again, Clojure sets are functions, so they literally do act that way. Vectors are maps from integers to values, specifically a contiguous set of integers. And finally, lists, which don't quite fit into this, but you can kind of finagle them in there. If you think of a list just has two keys, first and rest. So you can either get the first element of the list or you can get the rest of the list. So every data structure in a program is really kind of like a function that gives us some mapping from one domain into some range. And this is very useful as a way to think about data. One of the other nice things about maps is that they're open. You can add any number of keys onto the map, and you can keep adding them later. And in fact, you can do this in a way that will prevent collisions and clashes, because you can namespace your keys. So keywords as keywords as keys and then things as values is a very common way of representing data in Clojure. But we can make additional use of this map. We could reuse this same data structure in a bunch of different places and add information to it each time. Now, if we want to do that safely, we want to make sure that our keys don't clash, we can add namespaces to our keys. So, here I've added the business namespace for my key, which, by the way, does not have to match a namespace in my code. It could, but it doesn't have to. I'm just saying, okay, there's a business role, and, in my gaming system, there might be a role that represents a player or a dealer. Those are different kinds of roles, and I want to associate them both with this same object, this same record, without running into clashes. So once you start namespacing keys and protecting yourself in this way, you can almost always add more keys onto a map. It's never going to be a problem. And of course, the other fun things about maps in Clojure is that you can destructure them. You can pull the keys out by name. And I really feel like whenever you look at a function and you see it has more than 2 or 3 arguments, you can make a good case for just turning it into a map and passing a map in. There are a lot of advantages to that. I mean, one, obviously, is that you don't have to worry about argument order. You don't have to, get the arguments in the wrong place. So anytime you have a function where it's not necessarily obvious what order the arguments should go in, maybe you can just stick them in a map. And then you can destructure inside the function. It's frequently one of the advantages to this is that then you don't have to worry about any additional information. If there are extra keys added to this person object, that's not really a concern. They just flow through. They don't interfere with this function here. Now, of course, Clojure does allow you to do that destructuring right in the argument list, and occasionally that's useful, but I tend to avoid it. I generally find it's a little harder to just look at a function and see what the arguments are. So I think, this style of destructuring is useful for very small anonymous functions where you kind of know what the argument is. But I've lost some just semantic information from the previous slide. I no longer know that this function takes something that logically represents a person. All I know is that it takes some map that has first name and last name keys. So again, this is not bad. This certainly works, and it's perfectly valid, but I just find it a little bit harder to read, so I try to avoid it for top-level functions. So one of the things that people always do when they come to Clojure is they think, I want to define my data type. So they start writing def record everywhere, and I went through my def record phase too. So the thing is, we've been trained to think, again, through years of statically typed object-oriented languages and static database schemas and all these other things, that before you can talk about a piece of data, you have to declare all the fields. You have to define the shape of something before you're allowed to talk about it. But Clojure is a dynamic programming language. We almost never have to declare something before we use it. Why should we need to declare the fields in our maps before we start using them? This is really just an optimization for performance or other reasons, which I'll get into. But you might ask, okay, well, then how do I remember what the keys are? If I'm just using maps, and my map has 20 or 30 different keys for different attributes, how do I keep track of all those attributes and make sure that I don't, type the wrong name? And honestly, it's not that hard, so you could just put a comment at the top of your source file with an example of the data structure that you're working with. And then, if your editor is smart enough to do word completion based on the text in the file, then you can just hit tab to complete the names of the keys and give yourself a little bit of protection against things like typos. But even this declaration, just creating a record like this, is not going to protect you from mistyping the name of a key. It doesn't give you the same kinds of protection that static typing was intended to do. So you might as well just embrace that and just use a map. So you should always start with maps. Other people have said this, and I'm going to repeat it. Always, when you're designing or prototyping your code, always start with maps, and don't add records until you realize you need them. And as far as I know, there are only 2 reasons where you actually need records. Maybe 3. I mean, you could argue that there are some situations where you actually need a type, a concrete type, and that kind of ties into the polymorphism argument. Records do give some small amount of performance benefit, especially if you have a lot of them that are very similar, but honestly, I have never encountered a program where the difference between records and maps was a measurable performance bottleneck. Performance bottlenecks always end up being stuff like I/O, network, logging. So yes, there are situations where the map versus record performance difference might matter, but it's very unlikely, and it's not sufficient justification to try to define all of your types for your maps up front in records. There is another reason, though, that is a good reason for using records in place of maps, and that's when you want to add behavior to your records. But you only need records in that case if that behavior is actually polymorphic. Which brings me to my next point. So in Java, and in probably some other object-oriented languages, polymorphism is the default. Anytime you write a method in Java, it is virtual by default, unless you explicitly declare it final. So we've sort of been, again, trained to think that this is a good idea, that we should be doing this, that all our methods should be potentially polymorphic. It turns out the vast majority of them are not, which is a good thing, because runtimes like the JVM have a really hard time optimizing or inlining polymorphic functions. So when the JVM is optimizing your Java code, it tries to profile and figure out if a method is truly polymorphic or what it calls monomorphic, just has one potential implementation. And it's much better at inlining the monomorphic methods than it is at the polymorphic methods. But the more general thing with polymorphism, especially in Clojure, is do you really need it? So say, I do decide that I need a person record because I want the full name function to be polymorphic. I want the full name function to be defined on person. Now, if you're working in Java, this is kind of the only option you have. You have to hang your methods off of objects, but we don't have to do this in Clojure. Full name could just be a function. And it only needs to be a polymorphic function, a protocol function, if we actually think that there are going to be cases where we have different implementations of full name for different types of objects. So, what is the likelihood that we're going to have something, we're going to be calling the full name function on something that isn't a person? I don't know. Seems pretty slim to me. Moreover, what's the likelihood that we're going to call a function like full name on something that doesn't have first name and last name keys in it? That seems even more unlikely. So the fact that we can define our functions to just look at associative data structures that are dynamically typed gives us a lot more flexibility and means that we don't necessarily have to define this function multiple times for different types. We could just define it once in terms of keys, and then any record or map that has those keys would be a valid argument to the full name function. Turns out we really only need polymorphism if there's a situation in our code where we're going to call the full name function and we don't know what kind of object we're getting, where maybe we have a collection of a whole bunch of different things with different types, and we want to map the full name function across them. Then polymorphism really helps us. But the vast majority of the time, we don't need it. Another thing we've been taught is encapsulation is good. We've been told that we need to hide the representations of our data and actually access elements of that data through methods or accessors. Now, of course, you can do this in Clojure. So, the classic OO example is you have a circle object. Do you represent that circle as a radius or a diameter? So maybe you don't know. You're going to write a function called radius to pull out the radius and implement it for different representations of circle. But what if you had a whole lot of code that was doing some mathematical calculation with your circle, and those mathematical calculations always needed to use the radius? Well, then this suddenly matters. Because if you use the representation with diameter, you're going to be doing that divide diameter by 2 calculation every single time you access it. You're going to add a huge amount of overhead to your calculations just because you chose a representation that didn't actually fit the computation you needed to do. To take an even more extreme example that's pretty much standard in object-oriented languages, a linked list versus an array. You can have a linked list and an array implement exactly the same interface, and in Java they do, Java util list, but they have wildly different performance characteristics, and swapping one for the other is going to have a huge impact on your program. So what this boils down to is that representations do have consequences. We cannot just assume that by encapsulating them we have isolated ourselves or abstracted away the actual differences in representation. The other place where representations matter is anytime we want to send a representation from one program to another program, anytime we want to communicate over a network or even across processes. As soon as we do that, all of a sudden the representation matters. We have to agree at both ends of that communication what representation we're going to use. So any benefit we had from hiding that representation in our code pretty much goes away as soon as we have to do any communication with the outside world. So what I suggest, instead of encapsulating or hiding your representations, let your representations be visible and think about them. Choose the representation that best fits a particular module or program or component that you're dealing with. And then establish the boundaries between those components where representations can change. We change representations all the time. That's probably what computers do more than anything else. They transform data from one representation into another. And if you're clear about what representations you're using and where they change from one to the other, you can get most of the benefits of encapsulation or hiding without some of the penalties that it might incur. A really interesting example of this, in fact, is the new data literals feature in Closure 1.4. So this is a new thing. You'll be hearing more about it soon if you haven't already. But we now have the ability to extend the closure reader by writing something that looks like hash, then a tag, and then some other piece of closure data. So in this case, this is one of the built-in reader tags that will be there in 1.4, inst, I-N-S-T. Short for instant. So instant is specified by Closure to look like this, to be a string in this very restricted date-time format. It's a subset of the ISO date-time formats. And it must absolutely look like that. Whenever you want to print or read an instant, you have to agree on that representation. But you're allowed to have different representations that you use in memory. So one program might want instance as a Java util date. Another program might want a Java util calendar. Another program might want JOTA time objects. The choice of which representation gets used is up to you. You can change a dynamic variable or change a configuration setting to get a different object back from the reader when it encounters this representation. And of course, you can add your own new tagged representations under namespaced tags, namespaced keys, that allow you to, define a printed representation that is potentially isolated from the representation you use in memory. So the next big idea, this is the second big takeaway that I want you to get from this talk, and that is make your functions composable. Make sure that they can all just take one output and take it to the next input. Let me show you what I mean. When we start out writing Closure, everyone, including me, has written a function that looks like this. You write, defn something, and you've got all kinds of things happening in there. You get some dereferenced mutable state, you do some calculation on it, you call a bunch of other processes that might involve other state, and then at the end, you do some side effect. Maybe you change the state, maybe you do something physical in the world, who knows, but you do something. This is hard to compose. It's hard to test. If we wanted to test this, we'd actually have to set up the initial state and then examine the resultant state. There's a lot of, setup and teardown to test this. And it's hard to change. It's really hard to insert another step into this process without breaking some of the other processes. So in general, this kind of code is difficult to maintain, difficult to manage. Much better code would be something that looks like this. I've discovered that I really love writing functions that look like this. This is just the essence of programming in my mind. I have some input state, and then I'm going to call a bunch of functions on it. And if you're not familiar with the threading macro, the hyphen greater than sign, that is just a macro that nests function calls inside each other. So it's going to take my state, call the function subprocess1 on that state, then take the result of that and call the function subprocess2 on that, and then take the result of that, call the function subprocess3, and finally return the result of the whole chain. It's almost exactly like piping functions or piping programs in Unix. It's just sending the output of one function as the input to the next function. And writing code like this is very easy. This is easy to test, and it's easy to look at each of those functions in isolation. By the way, I'm assuming that each of those subprocesses is also a pure function. It could even be written with one of these threading macros to expand out into even more function calls. So I just have an old state as input, and I get the new state as output. Alan mentioned this morning, when you write code this way, it's very easy to just comment out one line of this and see what the result is by removing a single step. So this is a very fun way to write, and frequently that state will be some composite object, usually a map. And one of the neat things about that being a map is that I can accumulate more information. Each one of these subprocesses could add more information onto my state. In fact, if I wanted to communicate some piece of information from subprocess 1 down to subprocess 3, I don't have to do anything special. I just have to have some key that both those functions know about. It could be namespaced, or it could be a global key that I happen to know is unique. And then subprocess 1 can add that key in. Subprocess 2 ignores it completely. It just flows through. And then subprocess 3 will pick up that key and use it for whatever it needs. One of the big advantages of this, of course, is that this is how Clojure's own functions work. This is how all of the STM update functions work. So when I write my code as these pure functions from the old state to the new state, I can plug them in to any one of the mutable reference types because they all have the same behavior, a function that takes the old state and returns the new state. Another thing that I can do in a function like this is I can break the state down into smaller pieces. Remember I said that poker game that I showed, that had dozens of states, lots and lots of information and nested maps and nested lists and sets and so on. It was a pretty meaty, complex data structure. But a lot of the functions I was writing only needed to deal with one little piece of it. So rather than have code that has to pull out that piece and then call the function and then put the piece back in, I can just use the built-in structural navigation features of Clojure to do that. I can use a function like updateIn, which will take some value in my map that's under the key part A, take just that value, call the function subprocess A, get the return value, and stick it back in the map under the key part A. And I discover when I start working with, again, everything is a map, all my functions are pure transitions from old state to new state. I have a lot of functions that just look like this. I'm, piping my state through some transitions that operate on small pieces of it. Finally, the last lesson that I want you to get is to keep your side effects totally isolated from the rest of your code. And I'll show you an example of what I mean. So here's a little function. It does take some state as input, then it does some computation on that state. Maybe that computation takes a while, has to crunch some numbers. Then it checks some condition about the result of that computation. And if the condition is true, it launches a missile. If the computation is not true, it erases your hard drive. This is a difficult function to test. We'd either have to have an unlimited supply of missiles on our continuous integration server, or we'd have to resort to mocking. We'd have to mock out the launch missile and the erase hard drive functions. And we can do that. That's possible in Clojure. There are some tools and testing frameworks that help with that. But why do we need to do that? Why do we need to go in and break something about our code, actually change something about how our code works, just so that we can test it. So here's an alternative. I'll define my process as something that takes an initial starting state, and rather than returning some result of the computation, it's just going to add some additional information to the state. It's going to assoc something into the map. And then I'm going to define a function that just makes a decision. It doesn't actually launch a missile or erase the hard drive. It just decides which of those things should I be doing. And it returns a data representation for what the next step should be. In other words, it returns a description of what the program should be doing. And that description is just data. Now, here it's a keyword. It might be something more complex. It might be a map or a vector, a vector of tweets to send out or missiles to launch. Who knows? But the point is, this is a very easy function to test. I could just run this at the REPL and look at the results, or I could put it in my unit testing framework, or I could generate a bunch of tests for it and see what they do. I don't have to mock anything. Finally, in some other piece of the code that isn't dealing with the computation or the decision making, all it has to do is look at the result. It just looks and says, okay, what am I supposed to be doing? And I know there are only two possibilities. I'm going to launch a missile and erase a hard drive. Now, you probably still want to test this function, but you could do it under very carefully controlled conditions where you've hooked up a dummy missile launcher and a dummy hard drive, and you can do your integration testing with those external facilities hooked up. But your unit testing doesn't need to worry about that. It can just look at the computation and see if it's correct, which is usually the most important part. This is probably going to be calling some external API, doing some interop, who knows? It's going to be dealing with the outside world, and that always gets messier and harder to test. We know that. But we can make it easier to test the computational parts of our code by separating them from the code that makes things happen. So I just have a few conventions that I like when I'm coming up with names for functions. This is purely my personal preference. I'm not even really advocating this. This is just what I do that I've found to be helpful. Closure itself actually has 3 slightly different conventions for different side-effecting functions. Some of them are verbs, like print. Some of them have do on the front, like do seek, do run. And some of them have a bang, an exclamation mark, things like set or swap. And there are, there is some consistency to where those different conventions are used, and you can find your own conventions that are appropriate for your project. But the important point here, and what I think I would always recommend, is that side-effecting functions, things that are doing things in the world, should always return nil. You should never rely on those functions to return information, unless maybe it's like some status report about what happened along the way. Because, once you start using side-effecting functions to return data, then you start calling them in places where you didn't expect and getting side effects where you didn't expect. It's a big mess. So I said I would talk about testing, and I want to talk about different kinds of testing. Testing means a lot of different things. In the simplest case, there's the testing we do interactively at the REPL. We type our function in, we see if it does what we expect, and we work interactively that way. And we can formalize this into what I think of as single case testing, where we are going to explicitly write an input and explicitly write ourselves an output. We're going to say, okay, I know this function does something, and I want to validate that when I give it this input, it gives me that output. And this is very useful. This is a great way to test small cases, to check your assumptions, to check for edge cases or boundary conditions, things where you know there is likely to be a problem in your code. But this kind of testing, describing exactly what the inputs and outputs are, it gets a lot harder as your states get bigger and more complex. In that gaming system I talked about where there were dozens and dozens of keys in this multi-page data structure describing the state of the game, it'd be really awkward to write a test for that, where I had to actually, either copy and paste or try to handcraft all of those details. So there's some other options. One that I like, which I think is a lot of fun, is people have different names for it, but I like to think of it as enumerative testing, where enumeration means you are enumerating every possible input to your function. So here's an example. For that gaming system that I worked on, I had to write a poker algorithm. I had to analyze and score poker hands. Not a terribly complex problem, but there are a lot of edge cases, there are a lot of details, and I wanted to make sure I got it right. So I wrote my algorithm, I developed my poker hand finder, and I tested it in the REPL. I tried a few different combinations, and I printed out some of the intermediate steps it was going through, and I kind of got a good sense that it was correct. It seemed to be doing the right thing, but I wanted to know that it really was correct. So I went to Wikipedia, and I found the Wikipedia page for poker hands, and they had a list of all the possible poker hands and exactly how often they occur in a standard 52-card deck. So I said, okay, I can validate that the distribution of outputs I get from my function matches what this external reference says they should be. So I just took closure math combinatorics, and I took every 5-card combination from a standard 52-card deck, and I ran my poker hand function on it, and I used the frequencies function to count up the results. Now, this took a while. There are 2.5 million possible poker hands in a standard deck. But it didn't take that long. I profiled it with a couple of smaller sample sizes, and it seemed like it would be done in a couple of hours, so I started it running and I went to lunch. When I came back, I had these numbers. And lo and behold, I checked on Wikipedia, and these were exactly the numbers that Wikipedia said I should get. So this gave me a lot more confidence than any number of handcrafted unit tests that my algorithm was correct. It was actually doing what I wanted it to do. Now, of course, that may not be a test that I want to run on every commit, but the advantage is it's unlikely to break. A pure function, these are all just pure functions that my poker hand function is manipulating. It's just data in and data out. And it doesn't depend on anything else in my program. It's completely isolated. So basically, once it's right, and it's not ever going to break unless I either change the rules or change the input. The fact that we write tests, we say sometimes because we want to ensure that changing something in one place doesn't break something in another place. I think that actually reveals a profound lack of confidence in our languages and our tools. If we are so worried that making a change over here is going to break some piece of code over here, I mean, that's just terrifying. But if we have functional code that's isolated from other things, we can make that assumption that it's not going to break. But it turned out this code wasn't 100% correct. The algorithm was correct. But there was a very subtle bug in how it returned its output. It included a key with a nil value when it just should have left the key off. And we discovered that through a combination of simulation and generative testing. Now, again, you could give different names to these. You could talk about these in different ways. But from my point of view, simulation testing meant that I was going to try to simulate what my system would do, what the program would do, given some series of inputs. So remember I told you that the sequence of states in this game was just a sequence of data structures. The inputs were also data structures. When the user clicks a button, that produces a map that gets sent as closure data in a string to a server, and then it gets evaluated there and interpreted. So I could capture and log all of the messages that were being sent to the system in a typical game and then replay them, and even add special messages to set things like the random seed so that I could see, so that I could get a repeatable simulation for the test. So this was something we did. Again, now this goes back to handcrafting inputs. We started with an example script, and then we started tweaking it. We modified it. We tried different actions for the players, different initial card deals. And, things seemed to be working. And every time we defined a new series of inputs, we could print out another version of that big table I showed you at the beginning. So given any set of inputs, we could print out a nice formatted view of everything that would happen in that game, which was a heck of a lot faster than actually clicking on things in the UI and then trying to see that the game was working because of that. But this wasn't enough. It wasn't too hard to construct these examples, but we would have gone nuts if we tried to construct them by hand every time. So we added in some generative testing. Now, when I think of generative testing, I think of generating random inputs to the program, generating a series, maybe, of inputs that will describe a game in this case. So we wrote some simulation code that could start from some initial state. It might have been, an empty game where nothing had happened, or it might have been a half-completed game where we had set up certain conditions. And then we have a generator function. The generator function can actually look at the state of the game and decide what's going to happen next. So, for example, we have a generator function that can handle a poker game with 3 players where nobody folds. It'll just play through the game, everybody keeps bidding, and we'll see what happens at the end. Then we added a series of test functions, invariants, things that should be true all the time. So there are a lot more of them. I cut this down to fit it on the slide, but some of the things are like, the total amount of money on the table must remain constant. So in every state of the game, the amount of money on the table and all the players and, all the chips that are there should always be the same. If it's not the same, then there's a bug. Something went wrong. So each of those is a function that gets run across all of the simulated states of the game to verify that these assumptions we're making, or these things we believe should be true about our program, in fact, are true. Finally, we have postconditions. We have, things we want to check after we've run the simulation. What is the state after everything has happened? And we want to know certain things in that case. So you'll notice this is using closure.test. It does actually call, deftest and the is macro that I wrote forever ago, but it isn't really using a lot of the machinery of that framework. It's calling this simulation function, and the simulation function is specific to our application. It's doing all the work. So the simulation is going to check all of our invariants and all of our postconditions, and if one of them fails, it's going to generate a detailed error report that includes the inputs, what the generator produced, where we started, what all the states were. It's going to print out that formatted HTML game log so that we can examine the game to see where it went wrong. And it's going to save that in a file somewhere and just return something to the test framework that says there was a failure. So the point of this is you don't necessarily need special code to do testing. Testing code is code like any other, and it can do the same thing, and you can think about what kind of outputs will be useful. What information do you want it to produce? So finally, there are different kinds of validations you can do, and I'll go through these quickly because this is pretty obvious. There are, validation that happens at runtime, checking your inputs, checking that the user types something they're allowed to type. These are things that you have to handle in a normal code path. They're part of the normal flow control for your program. Then there's another class of assertions, which are things that you want to check if your code is correct. You actually want to know if your assumptions are right. Are there bugs? So you can do this by adding pre- and post conditions, adding assertions, or even throwing exceptions in your code because it's acceptable to crash. You want to know as soon as possible when these things fail. You combine that with some simulation testing, and you have a very detailed set of assertions that the assumptions you make in your code are correct. Finally, you want to validate properties of things. And this is something of a stylistic concern, but I think rather than checking the specific type of something, rather than checking something that you might know to be true. You might know that this function is going to be called with a person record type as its argument. But that's not really the important thing. The important thing is that the person thing that gets passed has keys, first name and last name. That's the thing you want to check. Because you might change the first thing. You might change person type, person record. You might pass in a map instead of a record. And it's not actually going to break your code to do that. All that you care about, all that matters for this function, is that it contains those two keys. So there are the big ideas. Make your data visible, your functions composable, isolate your computation and decisions from side effects, and establish boundaries where you can choose where you're going from your computational world to your side effecting world, or from one representation to a different representation. That's all I have. I work for Clojure.com, and if you're curious, I made these slides with a little tool that uses Emacs org mode and ClojureScript. I'll be happy to answer questions afterwards, but we're done now, so thank you.